Welcome! In this session, we'll be exploring problem number 888, titled Fair Candy Swap. This problem is a classic example of how to approach a problem involving arrays and mathematical reasoning. Stick around as we dive into the problem details and solve it step by step. In this problem, Alice and Bob each have a collection of candy boxes, represented by two integer arrays called Alice's eyes and Bob's eyes. Each element in these arrays represents the number of candies in one box. The goal is for Alice and Bob to exchange one box of candy with each other so that, after the swap, they both have the same total number of candies. To achieve this, we need to find one candy box X from Alice's eyes and one candy box Y from Bob's eyes such that the sums of their candies become equal after the swap. Mathematically, this condition can be simplified to the equation x, y equals sum Alice's eyes sum Bob's eyes / 2. This equation ensures that the difference between the two totals before the swap is distributed equally after the exchange. Our task is to return any valid pair x, y that satisfies this condition, and we are guaranteed that at least one valid answer will exist. The input to the problem consists of two integer arrays, Alice's eyes and Bob's eyes, which represent the number of candies in each box for Alice and Bob respectively. The output is an integer array, x, y, where x is a candy box from Alice's collection and y is a candy box from Bob's collection. Let's consider a concrete example to understand this better. If Alice's eyes is 1, 1, and Bob's eyes is 2, 2, the output is 1, 2. This means Alice can give up a candy box containing one candy, and Bob can give up a candy box containing two candies, satisfying the condition for equal total candies after the swap. For the first example, Alice starts with a total of 1 plus 1 equals 2 candies, while Bob starts with 2 plus 2 equals 4 candies. The difference between their totals is 4, 2 equals 2. To equalize, Alice can give up a box with one candy, and Bob can give up a box with two candies. After the swap, Alice will have 2 1 plus 2 equals 3 candies, and Bob will have 4 2 plus 1 equals 3 candies. Now their totals are equal, so 1, 2 is a valid solution. Similarly, let's look at another example. If Alice's eyes is 1, 2, and Bob's eyes is 2, 3, the output is again 1, 2. Here, Alice's total is 1 plus 2 equals 3 and Bob's total is 2 plus 3 equals 5. The difference is 5, 3 equals 2, and swapping a box with one candy from Alice and a box with two candies from Bob again results in equal totals. In the second example, Alice has 1 plus 2 equals 3 candies, and Bob has 2 plus 3 equals 5 candies. The difference between their totals is 5, 3 equals 2. Alice can give up a box with one candy, and Bob can give up a box with two candies. After the swap, Alice will have 3 1 plus 2 equals 4 candies, and Bob will have 5 2 plus 1 equals 4 candies. Both now have equal totals, so 1, 2 is a correct answer. In another example, where Alice's eyes is 2, and Bob's eyes is 1, 3, Alice starts with 2 candies, and Bob starts with 1 plus 3 equals 4 candies. The difference here is again 4 2 equals 2, and swapping a box with 2 candies from Alice and a box with 3 candies from Bob results in equal totals of 3 candies each. That makes 2, 3 a valid solution for this case. For the third example, Alice begins with 2 candies, while Bob starts with 1 plus 3 equals 4 candies. The difference between their totals is 4, 2 equals 2. Alice can give up her box containing 2 candies, and Bob can give up his box containing 3 candies. After the exchange, Alice will have 2 2 plus 3 equals 3 candies, and Bob will have 4 3 plus 2 equals 3 candies. This makes their totals equal, so 2, 3 is a valid result. The problem also provides constraints. The length of Alice's eyes and Bob's eyes can go up to 10,000, and the number of candies in any box can be as large as 100,000. Additionally, we are guaranteed that at least one valid solution will always exist. These constraints require our solution to be efficient and handle large inputs gracefully. Edge cases to consider include scenarios where Alice's eyes and Bob's eyes each contain only one element. As long as the constraints are satisfied, the solution must produce a valid result even in such a minimal setup. For larger arrays, where the size approaches the upper limit of 10,000 elements, the solution must be optimized to handle the input efficiently without excessive computation time. Finally, if the difference between the sums of Alice's eyes and Bob's eyes is very large, the solution must accurately compute the correct pair without causing overflow or performance issues. These considerations ensure that the algorithm is both reliable and scalable across a wide range of test cases. To solve the fair candy swap problem, the first approach we might consider is the brute force method. Here, we would systematically try every possible candy pair that Alice and Bob could exchange. For each pair, we calculate the new total candies for both Alice and Bob after the swap. Specifically, Alice's new total would be her current total minus the candy she gives up, plus the candy she receives from Bob, and we do a similar calculation for Bob. If these new totals are equal, we've found a valid solution. This approach is simple and intuitive, but it requires nested loops to check all combinations of Alice's candies with Bob's candies, making it highly inefficient. The time complexity is n*m, where n is the number of candies Alice has, and m is the number Bob has. Additionally, it has a constant space complexity, but the computational cost becomes impractical as the input sizes grow larger. To improve upon the brute force method, we can use an optimized, set-based approach. The key insight here is that instead of comparing every possible pair, we can use the difference in total candies between Alice and Bob to narrow our search. Let's define summa as the total candies Alice has, sum b as the total candies Bob has, and delta is half the difference between these two sums. For a successful swap, Alice needs to give up a candy, Alice candy, and receive a candy, Bob candy, such that the difference between them equals delta. Rearranging this, we find that Bob candy must equal Alice candy minus delta. Using this relationship, we can streamline the process. First, we calculate delta. Then, we store all of Bob's candies in a set, which allows for quick lookups. Finally, we iterate through Alice's candies and check if the corresponding Bob candy exists in the set. This eliminates the need for nested loops and drastically reduces the number of computations. If we find a pair of candies, Alice candy and Bob candy, that satisfies the condition, we can immediately return it as the solution. The efficiency of this approach lies in its time complexity of n plus m. Building the set of Bob's candies takes m, and iterating through Alice's candies takes n. The space complexity is m, as we store Bob's candies in a set for fast lookups. This method is highly efficient because it avoids the exhaustive comparisons of the brute force approach. By leveraging the average O(1) lookup time of sets, we ensure that the algorithm scales well even for large inputs. The optimized approach is not only faster but also clearer, as it directly targets the problem's mathematical structure. The critical breakthrough in solving this problem was recognizing that it can be reduced to finding a simple arithmetic relationship between the candies that Alice and Bob exchange. By using delta to define this relationship, we narrow the solution space to only valid candidates and avoid unnecessary computations. While the brute force method is straightforward to implement, it becomes computationally expensive for large inputs. The set-based approach, on the other hand, is highly efficient, though it does require additional space to store Bob's candies. This trade-off is worthwhile, as the significant reduction in time complexity makes this approach optimal. By combining basic arithmetic with efficient data structures, the set-based method provides both clarity and scalability, making it the best choice for solving this problem. The problem involves Alice and Bob, who both have collections of candy boxes represented as arrays, A for Alice and B for Bob. They want to exchange exactly one candy box each to make their total number of candies equal. To solve this, we need to determine if such a swap is possible and, if so, identify the specific pair of candy boxes to swap. Mathematically, we start by calculating the total number of candies each has, denoted as summa for Alice and sum b for Bob. After swapping a candy box A from Alice's collection with a candy box B from Bob's collection, Alice's new total becomes summa A plus B, while Bob's new total becomes sum B plus A. For the totals to be equal, this leads to the equation summa A plus B equals sum B plus A. Simplifying further, we derive a key equation, B equals A plus sum B summa /2. This equation is the foundation of our solution, as it connects the values of A and B that would result in equal totals for both Alice and Bob. We define delta as sum B summa /2. For the equation B equals A plus delta to work, two conditions must be satisfied. First, delta must be an integer, as candy boxes are whole numbers. Second, the value B equals A plus delta must exist in Bob's collection. With these conditions in mind, we outline the steps to solve the problem. First, compute the total sum summa and sum b, and calculate delta. Then, verify if delta is an integer. Next, we use a set for fast lookups by converting Bob's collection into a set b, which allows us to check for the existence of b in constant time. Once this is set up, iterate through Alice's collection. For each candy box A, compute the target b as b equals a plus delta and check if b exists in set B. If it does, return the pair, A, B, as the solution. If no valid pair is found after iterating through Alice's collection, return a failure case indicating that no swap is possible. This algorithm is efficient due to several key insights. First, the use of a set for Bob's collection ensures constant time lookups for the value b equals a plus delta. This avoids the inefficiency of a brute force approach, where we would otherwise need nested loops to compare all pairs of candies. Second, the derivation of the key equation b equals a plus delta simplifies the problem significantly. Instead of checking all possible combinations, we directly connect values of a and b through this mathematical relationship, reducing the process to a single pass through Alice's collection. Additionally, handling edge cases is critical to ensure correctness. For example, if summa equals sum b, no swap is needed because delta is 0. If the difference, sum b's summa, is odd, delta becomes non-integer, making a swap impossible. Duplicate values in either collection are also accounted for, as the set-based approach inherently avoids redundant checks. These insights together create a robust and efficient solution. To implement the solution, we use two primary data structures, an array for Alice's candy boxes and a set for Bob's. Alice's array is iterated through linearly, where we calculate potential swaps based on the equation b equals a plus delta. This operation has a time complexity of O, n, where n is the size of Alice's collection. For Bob's collection, we convert it into a set, which allows constant time checks for the presence of b. The space complexity for this set is O, m, where m is the size of Bob's collection. Next, let's analyze the overall complexity. Computing the total candy sums, summa, and sum b, takes O, n plus m, time. Building the set b from Bob's collection takes O, m. Finally, iterating through Alice's collection and performing constant time checks in set b takes O, n. Combining these steps, the total time complexity of the solution is O, n plus m, while the space complexity is dominated by the storage of set b, which is O, m. In summary, the algorithm achieves a total time complexity of O, n plus m, and a space complexity of O, m. This efficiency is made possible by leveraging mathematical simplification and optimal data structures, ensuring the solution is both fast and scalable even for large inputs. The approach avoids unnecessary computations and handles edge cases seamlessly, making it a robust method for solving the fair candy swap problem. This is the Python implementation for the LeetCode problem number 888, Fair Candy Swap. The goal is to help Alice and Bob swap exactly one candy box each so that they both have the same total number of candies. Step-by-step explanation asterisk. 1. Calculate the total sum of candies for Alice and Bob asterisk. The variables sum underscore a and sum underscore b store the sums of Alice's and Bob's candy collections, respectively. 2. Determine the difference to balance asterisk. The variable delta is calculated as sum underscore a, sum underscore b, // 2. This represents the difference that needs to be adjusted between Alice's and Bob's collections to equalize their totals after the swap. Dividing by 2 ensures we find the single candy box difference each must exchange. 3. Optimize lookups for Alice's candies asterisk. Alice's candy collection is converted into a set underscore a. This is done to enable O1 time complexity for checking if a specific candy box exists in her collection. For iterate through Bob's candies asterisk. For each candy box B in Bob's collection, we compute the corresponding candy box A that Alice would need to swap. This is given by A equals B plus delta. 5. Check if the swap is valid asterisk. If the candy box A exists in Alice's collection in set underscore A, then the pair A, B is returned as the solution, as this swap will balance their total candies. This approach ensures efficiency by leveraging set lookups and avoids unnecessary nested loops, resulting in a time complexity of O, n plus m, where n and m are the lengths of Alice's and Bob's candy collections, respectively. Here, we start by importing the necessary classes and defining our solution class. Within it, we have the method fairCandySwap, which takes two arrays, A and B, representing the candy sizes Alice and Bob have, respectively. The goal is to find one candy from each person such that swapping these candies equalizes the total candy each person has. First, we calculate the total sum of candies for both Alice and Bob using two separate loops, summa for Alice and sumb for Bob. Then, we compute the difference, delta, which is essentially half the difference between the two sums. This tells us how much needs to be adjusted to balance the candies. Next, we use a hash set to store Alice's candies, allowing us to check in constant time whether a specific candy exists in Alice's collection. This helps optimize our solution significantly. Finally, we iterate through Bob's candies. For each candy B in Bob's array, we calculate the corresponding candy A in Alice's collection that would balance the sums if swapped. If A exists in Alice's set, we return the pair as the solution. The solution concludes by returning the pair of candies that ensures both Alice and Bob have equal total candy after the swap. If the algorithm doesn't find a valid pair during the iteration, it means the input does not meet the problem's constraints, though this scenario shouldn't occur based on the problem description. In such cases, we return an empty array. This implementation is efficient because the use of the hash set allows for quick lookups, and the overall complexity is O, n plus m, where n is the length of A and m is the length of B. This ensures the solution is both optimal and easy to understand while adhering to the constraints and requirements provided by the problem. To solve this problem, we start with the given arrays A and B. In this example, Alice has candies A equals 1, 1, and Bob has candies B equals 2, 2. First, we calculate the total amount of candy each person has. For Alice, the sum is 2, and for Bob, the sum is 4. Next, we calculate the difference that needs to be adjusted so that both have equal amounts of candy. This difference, delta, is computed as the difference in their sums divided by 2, which gives us -1 in this case. Now, to efficiently check if Alice can give a candy of a certain size, we convert her array to a set. In this case, the set becomes 1. Then, we loop through each candy size in Bob's array. For the first candy size, B equals 2, we calculate the corresponding candy size that Alice would need to give, which is A equals B plus delta, resulting in 1. Since 1 exists in Alice's set, we know this swap works. Therefore, the solution for this example is 1, 2. In this example, Alice has candies A equals 1, 2, and Bob has candies B equals 2, 3. Once again, we begin by calculating their total amounts of candy. Alice's total is 3, and Bob's total is 5. The difference to adjust, delta, is calculated as sum underscore A, sum underscore B, divided by 2, which gives -1. After this, we convert Alice's candies into a set for efficient lookup, resulting in set underscore A equals 1, 2. Now, we loop through Bob's candies. For the first candy size, B equals 2, we calculate the corresponding candy size from Alice as A equals B plus delta, which equals 1. Since 1 exists in Alice's set, this swap works, and we can return 1, 2 as the solution. This ensures that both end up with equal amounts of candy. Here, Alice has candies A equals 2, 4, and Bob has candies B equals 1, 3. We start by calculating the total amount of candy for each. Alice's total is 6, and Bob's total is 4. The difference, delta, is computed as sum underscore A, sum underscore B, divided by 2, which equals 1. Next, we convert Alice's candies into a set for faster lookup, resulting in set underscore A equals 2, 4. Now, we consider each candy size in Bob's array. For the first candy size, B equals 1, we calculate the corresponding candy size from Alice as A equals B plus delta, which equals 2. Since 2 exists in Alice's set, this swap works, and we can return 2, 1 as the solution. This ensures both Alice and Bob end up with equal amounts of candy. Here, we analyze the time complexity of the solution for the fair candy swap problem. First, calculating the sums of arrays A and B is straightforward. Since summing an array of size n takes O, n, time, the time to calculate the sums of A and B is O, n plus m, where n is the size of A and m is the size of B. Next, we convert the array A into a set. This operation involves hashing and inserting each element, which is O(1) on average per element, so converting A into a set takes O(n) time. Finally, we iterate through array B. For each element in B, we calculate a value and perform a lookup in the set. Both the calculation and the lookup are O(1) operations, so iterating through all m elements of B takes O(m) time. These steps together give us a clear breakdown of the time complexity. Combining all the steps, the total time complexity of the solution is O(n plus m), for calculating the sums, O(n), for converting A into a set, and O(m), for iterating through B. Adding these, the overall time complexity is O(n plus m). Now, for space complexity, the primary contributor is the set created from A, which requires O(n) memory to store n elements. Apart from this, all auxiliary variables like sums and loop counters use constant space, O(1). No additional data structures or recursive calls are introduced, so the space complexity is dominated by the set, resulting in an overall space complexity of O(n). To put the current solution into perspective, we can compare it with a brute force approach. In a naive solution, we would iterate through all pairs of elements from A and B, checking if swapping them equalizes the sums. This involves comparing every element of A with every element of B, leading to a time complexity of O(n*m). However, this approach requires no extra data structures, so its space complexity is O(1). In contrast, the optimized solution drastically improves time efficiency by reducing the time complexity to O(n plus m), thanks to arithmetic properties and the use of a set for quick lookups. While this does increase space complexity to O(n), the trade-off is well worth the significant reduction in execution time. Finally, let's analyze the best, average, and worst-case scenarios for the algorithm. In the best case, the very first pair of elements checked during the iteration satisfies the condition. However, even in this scenario, the pre-processing steps such as calculating the sums and constructing the set still dominate, so the time complexity remains O(n plus m). On average, the algorithm will check about half of the elements in B before finding a valid pair, but again, the pre-processing ensures the overall complexity stays O(n plus m). In the worst case, every element in B is checked before finding a valid pair or determining no pair exists, yet the time complexity is still O(n plus m), because of the pre-processing's linear scaling. To confirm, the summation operations scale linearly with the size of the arrays, and set operations like insertion and lookup are O(1) on average, making the iteration over B O(m). These parts combine to give the final time complexity of O(n plus m). In this problem, there are a few common mistakes that can trip you up if you're not careful. First, ignoring edge cases like empty arrays or when the sum of candies for Alice and Bob are already equal is a frequent issue. It's crucial to validate inputs and explicitly consider the smallest possible cases to avoid runtime errors or incorrect results in unique scenarios. Another mistake involves incorrect swap logic, miscalculating the difference needed to balance the two arrays, or forgetting that the swapped values must actually exist in the respective arrays. Without ensuring these conditions are met, the solution will fail. Additionally, using nested loops for large inputs is another pitfall. A brute force approach may seem straightforward, but it performs poorly when the input size grows, often leading to timeouts for constraints like n greater than 10,000. Lastly, for those using binary search, not sorting the array beforehand is a critical oversight. Binary search only works on sorted data, so skipping this step will break the logic entirely and result in incorrect outcomes. Another common mistake to watch for is mishandling integer overflow, especially in languages like Java or C++. When summing up large arrays, exceeding the maximum value an integer can hold leads to unexpected behavior, so it's important to check for overflow. Now, from an interview perspective, there are some key insights to consider. At its core, this problem is about finding a pair of values, one from each array, such that swapping them balances the sums. Mathematically, this boils down to evenly splitting the difference between the two sums. This type of pattern, balancing or equalizing two sets, appears frequently in problems involving sums, differences, and searching for specific elements, like two-sum or subset problems. Optimizing your approach is another important aspect. Instead of brute force, you should focus on efficient solutions like using hashing for O(n), complexity or sorting with binary search for O(n log n). During interviews, it's also crucial to communicate your thought process clearly. Explain the trade-offs between time and space complexity as you justify your approach, showing that you understand the problem deeply and can make informed decisions. This problem is also connected to several related problems that can help you understand the underlying concepts better. For example, LeetCode 1.2 sum uses a similar hashing technique to find two numbers that meet a specific condition. LeetCode 560 subarray sum equals k is another example that focuses on difference calculations, but it uses prefix sums. LeetCode 1099 2 sum less than k deals with finding pairs of values under constraints, while LeetCode 416 partition equals subset sum involves balancing two subsets, which is conceptually similar but solved using dynamic programming. Alongside these related problems, there are alternative approaches to solving fair candy swap. The brute force approach, though simple to implement, involves iterating through all possible pairs of candies to check if swapping them balances the sums. While it's straightforward, it has a time complexity of n squared, which becomes impractical for large input sizes. On the other hand, the hash map approach allows you to store the difference between the target difference and each candy value, reducing the complexity to n. However, this requires additional space proportional to the size of the arrays, so there's a trade-off between time and space efficiency. Another efficient option is sorting one of the arrays and using binary search to find the required partner candy for each value in the other array. This approach runs in n log n due to the sorting step, and it can be an excellent balance between time complexity and space usage. However, it does require additional sorting logic, which may be harder to implement under time pressure during an interview. Each of these approaches has its strengths and weaknesses, so it's important to choose the one that best fits the constraints of the problem while also considering your ability to execute it effectively. By understanding these variations and trade-offs, you'll be better equipped to handle this problem and similar ones in both practice and interviews. That wraps up our solution to problem number 888, fair candy swap. We covered the problem, examined a brute force approach, and optimized the solution using hash sets. Don't forget the key takeaways: hash sets and mathematical reasoning can be powerful tools. Thanks for watching, and I'll see you in the next problem-solving session. Happy coding! That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!